You can see here that our eigenfunction is a function of our theta phi. So we will start our radial function. The radial equation is this. Alright, so we're gonna substitute for the 7 orbital. N is equal to 7, L is equal to 6. So there R to the L, 6. U is to the CR over 7A. Summation of n minus 1 is 1 minus 1, so 0. So therefore, we will not going to use any recursion relation here. Alright, so here r raised to 0 is 1, so it will vanish. So our general radial equation will be like this. Okay, so the next thing we're gonna do is normalize. So the normalization equation will be like this. Okay, next, applying the normalization, we have BO r to the 6 e raised to negative ZR over 7A squared. So yeah, r squared dr. Okay, combining both and taking out the constant outside the integral function, and then 1 equals BO squared, B sub 0 squared, the integral of r raised to 14e raised to negative 2 ZR over 7A dr from 0 to infinity. So according to the table of integrals, when we have this kind of function, the integral of that is n factorial over a n plus 1. So in our equation, the n here will be 14 and our a will be 2z over 7a. So applying that, we have 1 equals b sub 0 squared. So n factorial, 14 factorial over should be our a raised to 14 plus 1, 15. Rearranging this equation, alright, like this, then isolating b sub 0 squared, and finally getting the value of b sub 0. Wait, b sub 0. So b sub 0 would be substituting here. So finally, this is our radial function. Alright, so later we will use this. Okay, now let's go to our harmonic function, specifically our theta function. Right, so this is the formula for our theta function. So all we have to do is substitute the quantum numbers that we are assigned to. So this will lead to sine squared theta 4 over 2 summation of 6 minus 4, absolute value of plus minus 4, is it to be equal to 2. So our j will be bounded from 0 and 2. So our x, let's substitute the j there. So our j is 0, a is 0, cosine theta raised to 0 plus j equals 2, a 2, a sub 2, cosine theta raised to 2. So our cosine theta raised to 0 will lead to 1. Okay, next, so this will be our general theta function for this. Okay, now we will notice that we have two different variables here. So we have to write this a sub 2 in terms of a sub 0, so that when we normalize, we will not be facing too much trouble. Okay, so this is the recursion relation for that. Okay, so we all know that our j is equal to 0. So let's, and our m is plus minus 4, so this is absolute value. So and our L is 6, so substituting those, we'll have this a sub 2 is equal to negative 11 a sub o. So this will be substituted there. Okay, so this will be now our a sub o term theta. So rearranging that, or maybe distributing this, we'll get this, and I'm recommending to isolate a sub o first so that normalization will be easy. Okay, next is the normalization. So this will be our normalization equation. So substituting our theta there, so it will be a sub o, a sub 0, sine to the 4th theta minus 11 sine to the 4th theta cosine squared theta. So repeat it again, yeah, there, sine theta d theta. Don't forget this, many are being misleading there. So taking out the constants, so a sub 0 squared, so it's to you, and then using FOIL method here, we'll get this. I recommend to not yet include sine theta in our equation. We will further simplify this. Alright, now we are about to simplify our terms here. So using identities, you all know that sine squared theta is equal to 1 minus cosine squared theta. So meaning sine squared theta raised to 4 is equal to sine raised to 8. So if we have to raise this into the power of 4, we also raise this to the power of 4. So now we will use this replacement to sine raised to 8. So the equation will be like this. Okay, so I label this as first term, second term, third term, since we are going to expand this long, very long term. Okay, so expansion of the 1 minus cosine squared theta raised to 4 will be like this. Okay, be careful to not be wrong in expanding that, because it's so hard to be wrong. Joke. Next, after expansion of this term, we will now apply the functions that are next to it. Okay, so there we have to distribute this sine theta d theta here, so this will lead to this. Alright, next, it gets complicated, and you have to be careful in distributing the terms, because it will dictate if you're going on the right track or not. Alright, after distributing all those terms, so 1, 2, 3, we have to combine them all. Okay, there we have combined it, but take note that you have constant there in your terms, and you also have a constant here and there. So remember to, if you are distributing that and if you are going to expand it here, be sure to include those constant together. Alright, so there I labeled the terms that are in the same structure, so cosine squared theta, sine theta d theta. Okay, there they are labeled so that when we further simplify this, we will not be misleaded. Okay, alright, after 15 terms, we now have only 1, 2, 3, 4, 5, 6, 7 terms now. Okay, so next we will do the integration part of our equation. So I am following this integral. So cosine n theta sine theta d theta is equal to negative cosine n plus 1 over n plus 1. The trick here is we are only integrating this, so negative cosine theta, and it is combined here. So plus 1. So that. So there you have it. As you can see, I have this kind of fractions here. The n plus 1 is already taken out, so that when we evaluate this, we will not have any fractions. It's alright to do it. So evaluating those, we have this. It's all the same as you notice it, since the power of the exponent of the cosine function is odd. So if we evaluate those, it will just be the same. Alright. Okay. Next, getting the values of those. We have this. And further calculations, do this on your calculator na lang. We have this 1034 over theta 819. So there. Isolating a sub 0 squared, and then finally getting a sub 0. We can have this, or I prefer to do this so that the fractions will not be distracting. So finally, our theta function will be square root of 819 over 1024 sine to the 4 theta, quantity 1 minus 11 cosine squared theta. Alright, 2 down, 1 to go. Alright, we're down to our second part of our harmonic function, which is the phi function. So this is very simple. We only have to follow this formula, and remember the assigned orbital angular momentum quantum number for us is positive negative 4. We only have to substitute this in here and the m here. So therefore this will be our phi function, right? So now we have our completed. We now have the complete set for our eigenfunction on our 7i orbital. So combining these three, we'll have here our eigenfunction for our I orbital. Okay. So we all know that in this part, our function here is the configuration of the 7i orbital. And now we will do linear combination of atomic orbitals to further see the structure of each of those orbitals. Okay, so we will do linear combination of atomic orbitals. So this will be psi prime. Psi prime will be the combination of the eigenfunctions with the different orbital angular momentum quantum numbers. So there, we'll normalize the psi prime using this formula and expanding this. Expanding this, we'll get these terms, 4 terms. So my technique here is when the orbital angular momentum quantum number is the same, this will lead to 1, and when they are in the opposite signs, this will lead to 0. So there, 1 0 0 1, and then going here, 1 is equal to n squared. So the values there, we will just add it, and then we'll get 2. So isolating n, we'll have 1 over square root of 2 as our normalizing constant. So therefore our psi prime will be this. Alright, so as you can see, we have this. This means that E for I phi plus E negative for I phi. So we must eliminate the i's there. So to eliminate those, we will be using the Euler relation. So the Euler relation states that E plus minus I theta is equal to cosine theta plus minus sin theta. Therefore, our E for I phi plus p negative 4i phi will be equal to cosine 4 phi plus I sine 4 phi plus cosine 4 phi minus I sine 4 phi. So this will be cancel each other out. So p plus minus 4i phi will be equal to 2 cosine phi. Therefore, our overall psi prime will be equal to this 1 over square root of 2 over 1 over this will be the 4 phi factorial on the latter lessons. 2c over 7a is to 15 over 2 r to the 6 e raised to negative cr over 7a. So our theta function here, square root of 819 over 1024 sine to the 4 theta, quantity 1 minus 11 cosine square root theta. So this will be our phi function now. 2 over square root of 2 pi cosine 4 phi. Right? This is one of the orbitals in the 7i orbital. Okay, so we will do the opposite on the psi prime. So we will now subtract. So doing that, this is the same process, but the difference is that we get e 4i phi minus e raised to 4i phi. We get in psi prime, we got plus here, so now we will get minus since we subtract those functions. So using the Euler's relation, you will get 2i sine 4 phi. So substituting that in the phi function here, we'll get this, but we still have an I term here, so we must eliminate that. We will do normalization again for the psi double prime to eliminate the I. So here, the integral of negative I times I d tau will be equal to negative I squared, which is equal to 1. So therefore, our psi double prime will be like this. The only difference in psi prime is in this term. Okay, this is another term for the 7i orbital. Alright, so last step is to include the spin angular momentum quantum number, which is -1. It is also can be written as beta. So we only have to add this to our psi prime and psi double prime. So there. So this is the 7i orbital. Okay. I hope you understand. Sana po tama ako.